While predicting the price of a house based on its size is very nice, it does not describe what happens in our world. For example, the price of a house can be affected by the number of floors it has. And that's where multivariate linear regression comes in. To put it simply, it's just linear regression with multiple variables. Instead of having only theta 0 and theta 1 in our hypothesis, we now have theta 0 to theta n. Going back to the housing price example, for n equals 2, theta 0 might represent the basic price of house, theta 1 might represent the price per square meter, and theta 2 might represent the price per floor. Also, our hypothesis can be represented as matrix multiplication for x0 being 1. Gradient descent with multiple variables is just the same as with one variable, but instead of updating theta 0 and theta 1, we update theta 0 to theta n simultaneously. Going back to the housing price example, something you might have noticed is that the size of a house is usually a number with 3 digits or maybe more, and the number of floors is a single digit number in a private house. It turns out that the difference in the scale might affect gradient descent and slow it down. This is where feature scaling and minimalization come in. Feature scaling means adjusting the input values so they are all on a similar scale, like dividing them by the range maximum so they are all between 0 and 1. Minimalization means making the average value for each input roughly 0 by subtracting the average for each value. Sometimes a linear function won't fit our data well. In that case, we can use a polynomial function. We can change the behavior or curve of our hypothesis function by making it quadratic, cubic, or maybe use a square root function, or just any other form that matches our data. For example, if our data looks like this, a quadratic function that will match our data will be this one. And if our data looks like this, a square root function might match our data very well. One cool thing we can also do is combine features. Sometimes one feature is dependable on other feature. In this case, we can combine them into one. For instance, if we want our hypothesis function to ignore x2 when x1 is 0 and address x2 when x1 is equal to 1, we can introduce a new feature, x3, which is equal to x1 multiplied by x2, and end up with the following hypothesis. One thing to watch out for when using polynomial hypothesis is the range of our features. For instance, if our hypothesis is the following, and x1 has a range of 1 to 1000, then the range of x1 to the power of 2 becomes 1 to 1 million, and the range of x1 to the power of 3 becomes 1 to 1 billion, giving x1 to the power of 3 a great impact on our hypothesis output. While using gradient descent for minimizing our cost function can be really nice, it takes many iterations and it also requires us to select a good learning rate, which can be quite tricky at times. That is when normal equation comes in. Normal equation is a non-iterative algorithm that will minimize our cost function. Let's see how we can construct x and y using our training data. Let's say we want to predict the price of a house based on its size, the number of bedrooms, the number of floors, and the age of the home. In that case, given 4 training examples, x and y look like this. But what happens when x transpose multiplied by x is non-invertible? Well, there can be many causes for this problem, but the common causes are redundant features and too many features. Redundant features means that there are two features that are very closely related, which means that they are probably linearly dependent. Too many features is the case where the number of features is usually greater than the number of training examples we have. In this case, we might need to delete some features. Well, for now it sounds like the normal equation is just better than gradient descent. Well, that is not always the case. Since computing the inversion of a matrix has a time complexity of big O n to the power of 3, If we have a large number of features, the normal equation will be slow. And in practice, when n exceeds 10,000, it might be a good time to use gradient descent. If you like my summaries, I invite you to follow my Zero to Hero machine learning series, where I upload daily about my progression in AndrewNg's course.